Mayur Talele, and today I'll be presenting a novel deep learning algorithm to calculate and model the age-standardized COVID-19 mortality rate of a subpopulation when compared to a standard population. So there are many reasons to conduct the study. Primarily, there's the outbreak of the COVID-19 pandemic. In general, we have heat maps as shown in the middle, but we lack age-specific data through age standardization. So the purpose of this experiment was to create an algorithm to calculate and model death rates due to COVID-19 after age standardization. There's been important research regarding this field. Firstly, COVID-19 is a virus strain that has caused the pandemic. Thus, informing scientists and the public is vital. And specifically throughout the world, namely the US, there's been a lack of age-specific statistics and information being provided. And this is largely due to the fact that calculating ASMRs, or age-standardized mortality rates, are lengthy manual models, and ASMRs show the mortality rate after removing age discrepancies as a variable. So the overarching question for this project was, does age standardization remove the discrepancy in COVID-19 mortality rates in different populations? And based on this question, the objectives were to develop an efficient algorithm to identify the states with the highest ASMR and to investigate the role of age in deaths due to COVID-19. So the expected results were that there should be insignificant differences between ASMRs of different populations because age is considered the predominant factor in cause of death from COVID-19. To begin the experiment, the Python coding environment was installed, thus algorithm development and debugging could take place. Then the algorithm was tested. After the testing phase, the program was run using publicly available data sets for population and COVID-19 statistics in the US. And finally, statistical significance analyses were performed for program efficiency and ASMR calculations. The algorithm as shown was the one I developed using Python and deep learning techniques to produce the results of the study. So moving on to the results, the runtime of the program was calculated in 3 trials with 10 runs conducted within each trial. As you can see in the graph, the results, the runtime had a mean of about 3.5 seconds, and the error bars overlap each other, which shows that deviations from the normality is unlikely to occur. And most significantly, it is identified that the computer program runs efficiently and consistently with runtimes of near 3.5 seconds. Also, the crude mortality rate due to COVID-19 was calculated in various populations, and this is the death rate due to COVID-19 regardless of age or any difference. And as shown, there are large discrepancies. But although there are discrepancies, this would be expected to be neutralized after age is standardized. So the next graph shows the age-standardized mortality rate comparison of each population, in which the populations were adjusted to the age distribution of the standard population, which is the United States population. And clearly each hotspot state had a higher mortality rate than the US. When adjusted to the US population, each population still varied significantly, which shows that factors other than age must have been involved in causing the significant impact on deaths due to COVID-19. And similar to the ASMR graph, this is the expected number of deaths graph for each population. And in the graph, New York leads by far, which aligns with what we saw in the ASMR graph, showing that New York was most affected by non-age factors in causing deaths from COVID-19. The expected death calculations and models showed vastly different values and graphical trends, and therefore it can be ideated that other significant factors affecting death from COVID-19 must have occurred. So upon completion, the original hypothesis was not supported because most of the populations had statistically significant differences in ASMR. Furthermore, the algorithm had a consistent runtime of under 5 seconds, which meets multiple studies' definition of an efficient algorithm. And some of the limitations for the study included that some of the population and deaths from COVID-19 statistics were not updated at the time I obtained the data. And the applications for this algorithm are tremendous because this algorithm can be used for any other disease or any other condition where death is caused by age or seems to be caused by age.